Hi, I'm Junyoung Park from UIST, here to present our paper called Silent Impact Tracking Tennis Shots from the Passive Arm. So we're interested in how wearables and sensors are being used and integrated into sports. And there are now devices with all sorts of sensors providing a wide range of data about athletes and their activities, such as travel distance, body postures, muscle activations, and so on. And these devices come in various forms, from vests with GPS trackers, which are being widely used by professional football or basketball teams these days, to sensors embedded in gloves, goggles, bands, straps, and whatnot. Essentially, any gear in sports is considered as a candidate for a new sensorized product. And tennis has also seen its share of devices and wearables, with even major tennis brands like Wilson developing a few. Typically, they come in forms of bands that you wear on the wrist of your dominant arm, or as specially designed attachables that you attach to the string or handles of the racket. And these devices typically measure your racket swing movements through IMUs and provide data regarding your tennis shots, such as the types or the total count of shots you executed. And some more advanced features also estimate the power or spin of your shot, or how close to the center of the racket that the ball hit. But most of these products have now been discontinued, and a common concern raised about them was the discomfort caused by the sensor placement. Sensors are always placed somewhere on the dominant arm in order to capture measurements as close to the primary area of action as possible. But in practice, placing sensors on the racket strings or handles affects the weight, balance, and feel of the swing, and sensors around the hand can interfere with grip or restrict wrist movement. And combined with the hassle of acquiring or setting up the equipment, these issues ultimately discouraged recreational tennis players from adopting such products. So here we thought, what if we measure from the other arm? After all, people tend to wear smartwatches or watches on their passive arm, right? And we conducted a preliminary survey on watch ownership among the recreational tennis players, and out of 40 participants, all the watch owners wore their devices on their passive arm, and with the majority of them keeping it on while playing tennis. So if we measure movements from the passive arm, and if that can be done using sensors in smartwatches, we'd be able to eliminate the discomfort and inconvenience associated with traditional sensor placements. So that's what Silent Impact is. It's a smartwatch-based application that uses the IMU sensor in a smartwatch to measure the movements of the user's passive arm during tennis and track all the shots the user executes. But recognizing tennis shots from the passive arm especially isn't so simple, because players move their passive arm in different ways, even when executing the same shot. For example, from the dominant arm, in a forehand stroke, your arm would always be moving forward, it would hit the ball, and then it would move up and around your body. But for the passive arm, because it doesn't directly influence your shot, some may pull the arm in towards the body, while others extend it out and rotate it out. So, and in fact, even the same player can also show different movements depending on the speed or height of the incoming ball. So we wanted to investigate the potential of using the passive arm and using the movements of the passive arm as proxies for those of the dominant arm. And so we first collected IMU data from 20 recreational tennis players in our institution with varying levels of tennis experience. We used only IMUs since they are commonly found in many smartwatches and fitness bands. And for data collection, we used the X-Sense dot, and participants wore the sensors on both wrists so that we can use that data to capture the exact moment of the shot for labeling and also to compare the performance when using data from either wrist. And we collected data targeting two different tasks. For the shot classification task, the goal is to classify a given shot instance into one of the 6 shot types. We chose the forehand and backhand strokes, forehand and backhand volleys, smash, and serve. And we collected this data in a ball feeding setting, which means that someone else hit the ball from the other side of the net to the participant in a consistent manner so that the participants could perform the shots that they intended. And for each participant, we collected 50 shots for each type, resulting in 6,000 shots in total. And for shot detection, the goal is to detect the moment when a shot occurs. And for this, we recorded the data while participants engaged in tennis rallies or casual matches. And this resulted in a total of 368 minutes of data, or around 2,200 shots. We then developed neural networks for each task. For shot classification, prior work on using the dominant arm data for tennis shot classification has shown that just a few layers of convolutional neural networks is enough to accurately classify shots. But because we're doing it from the passive arm, we built upon this model so that it can capture the most out of the data in the passive arm. And our model so decomposes the INU signals into 3 frequency bands using the Fourier transform. And the goal is for each band to capture the movements at different aspects of the body. So the lowest band targets larger whole body movements. The middle band targets upper body movements like arm swings. And the highest band targets minor vibrations that are transmitted around the body. And for shot detection, prior studies typically used shot peak detection and thresholds and they relied on the jerk that was caused when the ball impacted the racket. But since we won't have that from the passive arm, we needed to use the context surrounding each shot to distinguish whether something is a shot or not. So we used the MSTCN, which is actually a CNN-based model originally designed for the task of action segmentation. And this network is effective in capturing both long and short-term dependencies within sequential data, which would be beneficial for us as it can hopefully identify subtle movement patterns that indicate a shot. So with these neural networks and the data we collected, we then developed an end-to-end prototype application consisting of a smartwatch app for data measuring, a server for data processing, and a smartphone app to display the results. When the user starts the app on the watch, it begins recording accelerometer and gyroscope data. And once the user stops the app, it sends that data to the server, and then the server does all the processing. And once the server has detected all the shots and classified each detected shot instance, it sends the results to the smartphone to display a timeline of the shots along with a count for each shot type. The screenshot is shown on the right there. So here's a short demo of the system in use. Please note that although it does look like the data is processed in real time, it isn't, and we just align the post-processed predictions to match the timing of the video so that we can show it in this video. So to verify the effectiveness of the passive arm, we compared the models trained on passive and dominant arm data. For both tasks, we conducted 5-fold cross-validation, ensuring that data from different participants was used for training and testing. And each shot was represented by a window of 180 frames, or 1.5 seconds, with the ball strike aligned at the 1-second mark. The graphs on the right are the accelerometer plots for a single shot instance measured from the dominant and passive arms. And here are the results for shot classification. We compared our model with FCN, the original model that we built upon. And for FCN, there is a 9.1% performance gap between the dominant and passive arm data. And in contrast, our model, with its frequency decomposed modules, it improves the accuracy on passive arm data by 6.8%, reducing this gap. And the confusion matrix shows that the two arms caused misclassifications in different shot types. The passive arm data struggles more with distinguishing smashes from forehand strokes, while dominant arm experiences greater difficulty with serves. For shot detection, the performance difference between traditional peak detection methods and our model isn't that significant when using the dominant arm data. But for the passive arm, peak detection's performance drops drastically, while our model is still able to perform at a similar level. And looking at the plots, we see that data from both arms suffer from false positives and negatives throughout. For example, forehand volleys tend to involve the passive arm less, which leads to them not being detected from the passive arm. On the other hand, a player picking up a ball on the floor with the racket is predicted as a shot when using the dominant arm. Or when the ball is hit softly, the dominant arm doesn't detect a jerk, while the passive arm still shows patterns that correspond to a shot. And we also conducted a few ablation studies, which I'll go through briefly. First, when we tested the shot classification on shots that were executed during rallies and matches instead of ball feeding, we found that the accuracy, the performance drops a little because such shots involve rigorous movements such as running and jumping. And secondly, in our work, we used windows of 1.5 seconds, and of course, reducing this window size would decrease the performance quite significantly, but increasing this window size did not alter the performance by any significant amount. And then fine-tuning with the user's data, of course, greatly improved the accuracy for a user. So this could be helpful in applications. And finally, using lower sampling frequencies, we used 120 hertz, but when we tested with 30 or 60 hertz, it didn't impact the performance that much, which could be important when power consumption or the quality of the IMU is an issue. And finally, we performed a user study to see how people perceived using our system compared to when using systems that require the watch on the dominant arm. All participants experienced both conditions and played tennis rallies or matches for at least 5 minutes with each condition. And after the session, they were asked about the mental and physical burden in the setup process to use the system and playing with the watch on. And the results show that participants felt less physical and mental burden using our system for both setup and tennis play. For the setup process, those who already wore smartwatches, all they had to do was tap start on their smartwatch. So it's quite reasonable. And during play, since all participants weren't accustomed to wearing a watch on their dominant arm, they all found the device physically cumbersome. Meanwhile, even the 3 participants who didn't regularly wear watches reported that having the watch on the passive arm didn't feel as distracting on the wrist. So what does our work mean for tennis? Well, of course, we should look into what more we can infer from the data from the passive arm. But honestly, advanced metrics like shot power and shot spin don't seem as plausible from the passive arm. But with more data, if we find patterns in the context of the data, or we explore other modalities existing on smartwatches such as audio or biosignals, maybe we can at least get discrete categorization of such advanced metrics. Besides, creative applications from the simple feature of just tracking shots can lead to creative applications, such as one-on-one competitions or collaborative trainings with multiple users, can lead to wide adoption just because using it is so natural and comfortable. Which leads me to the next point. Where else could this concept of using subsidiary motions as proxies be applied? Other sports with larger movements, of course, such as basketball, golf, or badminton, they may also show meaningful information in the passive arm. But more importantly, any location on the body could be used. And rather than only considering where the most accurate measurements can be made on the body, we should now also consider how comfortable such locations are, and also what devices that people are already widely using exist on such locations. So with that, I will end my presentation. Thank you for listening.
I'm Hiroshi from MIT Media. It's very, very interesting ideas you tested. Then that inspired me because I remember the half QWERTY keyboard. Do you know? Chopping a keyboard into half, but still people learned in a dominant hand or non-dominant hand can be transferred. People can still type using certain stuff. So my question, very crazy question, but you said dominant hand, passive hand, but some player use both hands. They can switch baseball or tennis, but some people may lose the injury, for example, cannot use dominant hand. Then they may want to continue to play in the other hand. So do you have any thoughts about the transfer of the knowledge or experiences between 2 arms?
That's a very interesting point that I haven't really thought about deeply. But for our work, we also had, for example, left-handed people and also people who wanted to wear the watch on the dominant arm. So we had to pretty much support all 4 types of arms, like left-handed, passive, left-handed, dominant, etc. And so, but for that, for our work, we would need data for each type of arm. And I guess that could be, but future works could work on how data collected on only one side of the arm could be used as, and transferred into other arms as well.
I think it's very interesting if you can find a player, they can switch both hands, then they collect the data. Then even have an implication for how people can continue to play even they lose one limb. Thank you.
Thank you.
Hi, this is Haoje from CMU. So I have a question on the part you mentioned, the different body motion corresponding to different frequency bands. So can you talk more about the intuition or empirical evidence behind that?
So we don't have empirical evidence within our model, but when we chose the band frequencies, we referred to prior works on, like, for example, walking and running are normally considered under the 4 Hertz range. And then all body movements that we can do with the body are considered under the 20 Hertz range. So we considered prior works on human motion and frequency when we chose the bands. And also, the modification that we made didn't increase the model capacity. So, like, you know, people could think, oh, you just increased the model capacity, that's why there are improvements there. But the two had the same number of parameters, and still it showed the improvement, which doesn't prove it, I guess, but does show a positive view of it. Thank you for your question.
Okay, thank you, Jun Yong. And